Alright guys, today we're going to be looking at planes, intersection angles, and I'm going to do a couple of different videos on this to kind of get us introduced to a few different ideas. Now what I've done is up here at the top I've written a couple of things that we should already know. We should know the dot product, and that is related to cosine, and then we've got the cross product, which is related to sine, multiplied by the by n, which is the normal vector, so that gives us the direction so that it's normal, but then you've got the magnitude, and then I've got the algebraic definitions of those, and I've also included here the equation of a line, of a plane. This is vector equation of plane that starts with any point in the plane and then two other vectors that are in the plane. As long as those vectors are not collinear, that will tell us where we're going from our point, and then it will spread out from that line. Okay, so that should then give us a plane, the definition of a plane. So what I want to do right now is just show you a couple other ideas that will be helpful. Okay, so right now we're looking at a plane. This plane contains vector AR, so that's inside of our plane, and then we got the normal vector, which is going perpendicular to the plane. So let's just define A. We're going to try to keep this pretty general for just a second. A will be x, y, z, and then R will be x1, y1, z1. And then N will just be a vector that is A, B, C, again, very general. Now, one thing that we need to note is that AR is perpendicular to the normal vector. So if AR is in the plane and the plane is perpendicular to N, then any vector that's inside of this plane will be perpendicular to N. So technically these are orthogonal, but if they were right on top of each other, they would be perpendicular. Okay, so because they're perpendicular, we know something about the dot product. The dot product, when it's perpendicular, will be equal to 0. So we're going to go dot product of n is equal to 0. Now to get AR, what we do is we actually take the vector r and subtract vector a. So vector r is x1, y1, z1, and we're going to subtract vector a, which is x, y, z, and if we dot product that with the normal vector, which is a, b, c, then we should get 0. Okay, so now the dot product can actually distribute. That's one of the nice things about dot product, is it's commutative, it's associative, it distributes. It follows most of our normal multiplication rules. So if we distribute this, it's going to go to both of them, and then I'm going to add the x, y, z to the other side, which will leave me with x1, y1, z1, dot product a, b, c is equal to, and if this moves the other side, it'll just be x, y, z, dot product a, b, c. Okay, which is an interesting little rule there, but it just means that the dot product of the normal with any direction vector inside the plane should end up giving you the same number. Now that would be helpful in the situation that, let's say that I'm given a point. So given point A, which is -1, 2, and 4, and let's say that the perpendicular vector, or n, is 1, 2, 3, and we want to write a Cartesian equation for the plane that includes this point that has that normal vector. So what we can do is, using this idea right here, we can just write the point and go -1, 2, 4, and dot product with 1, 2, 3, and that should be equal to x, y, z times 1, 2, 3, dot product, of course. I don't know why I keep putting that line there, but just 1, 2, 3. And so I can do the dot product here. -1 times 1 is -1. 2 times 2 is 4. And then 4 times 3 is 12. And then on this side, I've got x plus 2y plus 3z. So of course then I just end up with 15 is equal to x plus 2y plus 3z, which is then a Cartesian equation for a plane that then obviously includes that perpendicular vector and includes that point right there. So that's pretty nifty, I think. But one thing I want you to notice is that the coefficients of the Cartesian equation are the same as the direction vector of the normal vector. And that's going to be something that will be very helpful because that is always the case. If you have the Cartesian equation, you also know what the perpendicular vector is. And we'll be able to use that as we work through a couple of problems in one of the other videos. Okay, so we're just going to skip up ahead just a little bit. We're going to try another problem. What we're going to do now is we're going to find the parametric equation of the line through -1, 2, 3, and 2, 0, -3. And hence, we will find where the line intersects the plane x minus 2, y plus 3z equals 26. Alright, so let's go ahead and see if we can figure out how to do this. Now what we're going to do first is we're going to start with creating the line. Now the line won't be too bad because we already know that we can use a vector equation, x, y, z, which is your r, is equal to a, which is your starting point. So that can be either of these. It doesn't really matter which one you use. I'm just going to use -1, 2, 3 because it's there. And then we've got plus, and then we've got our direction vector times our parameter. Now the direction vector we're going to need to get from the combination of both points. It doesn't matter if you do AB or BA, so I'm just going to do BA, so I'll do 3 minus -3, which should be 6. I'm going to do 2 minus 0, which would be 2, and I'm going to do -1 minus 2, which would be -3. And so now I have a direction vector for my line. And so I've got it in vector form, and now I want it as a parametric equation, which is very easy from vector form. So I just write x equals -1 minus 3 lambda. So x equals -1 plus -3 lambda, or minus 3 lambda. I've got y equals 2 plus 2 lambda. And then I've got z, which is equal to 3 plus 6 lambda. All right, now from there we're going to be able to put it together, and if you want you can use a different parameter here. You can use t or n or some other letter, but I'm just using lambda for right now. And so now I've got my parametric equations. Now the nice thing about the parametric equations is that they relate each of your Cartesian variables to a single parameter. Now that's helpful because I can't really solve this equation for the plane. But when I find an intersection, what I do is I put one equation into the other one and then solve, and that finds out the position where they cross. So that's what we're going to do. We're going to put x in for x, we're going to put y in for y, and we're going to put z in for z. And you'll notice that when I do that, I end up with -1 minus 3 lambda minus 2 times 2 plus 2 lambda, and then plus 3 times 3 plus 6 lambda. And the only variable I have left now is lambda. And so I can go ahead and solve. First I'm going to need to distribute all that stuff. So I'm going to have -4 minus 4 lambda. I'm going to have plus 9 and plus 18 lambda. And that will be equal to 26. And so if I put all these together, I got a -3, a -4, which is -5, and 18. So that's going to give me 11 lambda. Got -1 and -4, which is -5 plus 9, so plus 4 equals 26. And so then I'm going to subtract the 4 to the other side, which will give me 22, divide by 11, lambda equals 2. Now I'm not quite done yet, because now what I need to do is I need to take lambda equals 2, and I want to find where the line intersects. So I can take lambda 2 and either put it into one equation or the other, but the easiest thing would be to put it straight into this equation for my line. So x, y, z, which is some location on the line, is equal to -1, 2, 3, plus -3, 2, 6, and we're going to put lambda equals 2 in. And so from there I should be able to get each of the points. So negative 1 plus 3, negative 3 times 2, so negative 3 times 2 is negative 6, plus negative 1 is negative 7. And then for y, it's going to be 2 times 2, which is 4, plus 2, which is 6. And then for z, it's going to be 6 times 2, which is 12, plus 3, which is going to be 15. And so I've got my intersection, x, y, z. And that right there is the point where the line crosses through the plane, because the lambda gave me the exact position on the line starting from the starting point that I chose, and therefore I now have the intersection of the plane. Alright, so that's our first video. If you want to stop it and go on to the next one, that would be pretty awesome.